So in this lecture, we would be discussing the EOQ, inventory management model. So EOQ stands for economic order quantity. And basically what this model does is it tries to give us an optimum order quantity. And that order quantity is the one that minimizes total inventory cost. And that is the basic purpose of this model. The basic function that EOQ model performs is it provides us with an order quantity that minimizes total inventory cost. So let's start our discussion. Now in this lecture, I will keep on referring to this example again and again. So let me first explain what the example is. So in this example, we assume that our lot size is 350 units. So lot size is the amount of units that we generally order from an organization. So for example, if we have an item X, Y, Z, and we want to order it from a supplier, if we order it in 350 units, so 350 units, if we generally order 350 units every time, then 350 units is what we call our lot size. Lot size is your typical order size. So, so the lot size, which is represented as Q, is 350 units. That is our order size, or that is our lot size. We will assume in this example that the demand is 50 units per day. Now, this is what we will assume, that our daily demand is 50 units per day. And as you notice, this is fixed. So this is not the average demand, this is the actual demand. So we are not assuming any change in demand, which is an assumption, but we will relax that assumption later on when we go to more complex inventory management models. For the time being, we are assuming that our demand is fixed at 50 units per day, and lead time is also fixed at 2 days. So lead time is 2 days, which means if I place an order today, I will get my items in 2 days. That is essentially what lead time is. So I'm going to clear the order point in a minute. Let's first take this information. So let's say we start with 350 units on day 0. This is, so on x-axis we have time, on y-axis we have the quantity. So we start with 350 units on day 0. Every day we use or we sell 50 units. And ideally on day 7, we will reach 0 units, right? Essentially, that's how it will be. So we'll start with 350. Every day we will sell 50 units. So which means at the end of day 1, we will be left with 300. At the end of day 2, we will be left with 250, and so on and so on. It will keep on reducing by 50 every day. And on day 7, we will reach 0 units. That is essentially what will happen, right? Now, ideally, on day 7, we should receive another 350 units, or we should have another 350 units in stock, and then the same cycle will start again. And on day 14, we will again reach 0 units. Now, if this is the case, and since our lead time is 2 days, we should place our first order on day 5. Because if we place an order on day 5, by day 7, we would have received those 350 units. Now, when we place the order on day 5, how many units do we have left in stock? We have 100 units left in stock, right? These 100 units will serve as our stock that we need to cover our demand for the next 2 days, right? So again, I'll repeat. These 100 units will serve the purpose of fulfilling the demand for the next 2 days. And these 100 units, or this point over here, is called the reorder point. or for my undergraduate students, it's called pipeline inventory. Okay. So in other words, basically what we are saying, as soon as our inventory touches 100, we will place a new order, right? That is essentially what we are saying. So then the cycle will keep on repeating. On day 12, you'll place your second order, and then 7 days after, which is day 19, you'll place your third order, so on and so on and so on, right? So this is the core example that we will keep on using in developing a basic understanding of our EOQ model. So let's move to the next slide. Let me clear all drawings. Now, excuse me. So as I said earlier, economic order quantities, the EOQ model or the economic order quantity model gives us the lot size Q that minimizes our total inventory cost. Now, generally, when we talk about inventory costs, it has three big heads. One component of inventory cost is the cost of carrying inventory. I have a slide later on that will discuss carrying cost in detail. The other component of inventory cost is the cost of ordering. And again, I have a slide on this as well. The third component of inventory cost is the expected stockout cost. Now, in EOQ model, there are no stockout costs. Why is that? Again, I'll repeat my statement. In the EOQ model, there are no stockout costs. The reason why there are no stockout costs is because there are no stockouts in an EOQ model. Why are there no stockouts? Because the demand is fixed and the lead time is fixed as well. So since we are not assuming any changes in the demand, since we are assuming that there are no changes in demand and no changes in lead time, that's why there is no chance of a stockout happening. That's why in EOQ model, generally in an EOQ model, there is no stockout cost. So then the only two costs left are the cost of carrying and the cost of ordering. And the EOQ model helps us strike a balance between these two costs. And that is what I've written here. The two main cost factors, if there is no variation in demand or lead time, are these two. And the EOQ model will help us balance out this versus this. Fair enough? So let's move on to the next slide. Now, as I said, there are three different cost components of inventory. The first one is inventory carrying cost, or also called holding cost. Now, this cost is proportional to the quantity of inventory held. The more inventory you will have, the higher will be your holding cost. So the components of this are the storage cost, the handling cost, and the opportunity cost of capital. Now, what do I mean by this? The more inventory you will have, the bigger the warehouse you will need, right? The more inventory you will have, the more people you will need, the more machines you will need to handle that inventory. Your product will deteriorate more. And one big factor is the opportunity cost of capital, right? So the more inventory you will have, the higher will be your opportunity cost of capital. So what do I mean by this? For example, if I have $200 and I invested all those $200 in inventory, I have lost the opportunity to use these $200 somewhere else in my business. So that is essentially called the opportunity cost of capital. Obviously, in the world of finance, this is slightly more complex, but I'm just giving a very simple example of opportunity cost of capital. So all these are components of holding cost, but the overarching rule is the more inventory you hold, the higher will be these costs, and that is represented by this relationship. So let me first place the drawings. The more quantity you hold in stock, so the higher your quantity, the higher will be your holding cost. So this again, we have two axes. We have quantity, order quantity on the x-axis. We have cost on the y-axis, and holding cost is the more inventory you hold in stock, the higher will be your holding cost. So it's directly proportional relationship. Now, the next component of cost is what we call the ordering cost or the setup cost. So the ordering cost is the cost of placing an order. So whenever you place an order, there's a cost associated with it. Those costs generally include components like bookkeeping expenses, order processing fees, transportation costs, receiving costs, handling costs. So what do we mean by it? So whenever I'll place an order, so someone will have to enter that order. Then suppliers are obviously going to charge me a price for picking the orders, loading the orders in their trucks, sending those trucks to me. So basically, the cost will include the cost of picking the items, the cost of transportation, the cost of salaries for the drivers. And then when I receive that order in my warehouse, I will have to offload the items. I'll have to place the items in the warehouse. So all of those costs, which include the handling costs, receiving costs, they come under the umbrella of ordering costs. So the more orders we place, the higher will be our ordering costs, right? So I'll again repeat, the more orders we place, the higher will be our ordering cost. However, higher number of orders result in smaller order quantities. Now, what do I mean by this? So again, to explain this, let me use the example, or let me take help from a graph. And let's take a hypothetical example. Let's say the demand, the yearly demand for a product is 1,200 units per year, right? So basically the demand is 1,200 units per year. Now, I'm going to draw a small chart over here, a table. So Q is my order quantity. And over here, I'll write number of orders. And I will also write the ordering cost, total ordering cost. Okay, let me erase this because this is not that good. Let me erase all of it. Let me make this again. Okay. So I'm going to draw a small chart. So basically, I'm going to write order quantity, which is Q. I'm going to write number of orders. And the third column is ordering cost. So let's say whenever I place an order, my cost of a single order is $50. So essentially what I'm saying is whenever I place an order, it costs me $50 to place that order. And that cost includes all these components, right? So now, if I place an order of 1,200 units, right? So the demand for the entire year is 1,200. If I place an order of 1,200 units, how many orders will I place in a year? And the answer is 1, right? I'll only place 1 order, and my ordering cost will be $50. And that will be represented by this chart. So 1,200 over here, let's say this is quantity. Let's say this is time. That will be something like this. I'll just place 1 order and I'll use that for inventory for the rest of the year. Now, is that a good way to go about it? Most likely not. But again, it's a hypothetical scenario. So let's say the management says, no, this is pretty bad. We have to have very big warehouses. Let's place an order of 600. Now, if we place an order of 600, how many orders do we need? In a year, we need 2 orders. And now our cost goes up to 100. So how will this look like? So 600 is half of 1,200. It will look something like this. Roughly this. first and second, right? Again, the demand is fixed at 1200. So basically this is how it will look like. And I'm just going to change the color. So let me use green. Let's use green. Okay. So now even we are, I mean, let's say we are still not happy with this. So we'll say, okay, let's say we'll place a very small order of 300 now. So let's say we place an order of 300. How many orders will we place in a year? To fulfill the demand of 1200 units in a year, we will place 4 orders and our cost goes up to $200. So 300 would be something like this. So 1, 2, 3, and 4. And just for comparison purposes, let's say if you place an order of 100, we will place 1200 orders and the cost will be $1200. So then that would be, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Cost of 100, cost of 300. Now, why did I do this? The reason I needed to do this is because I wanted to clarify this relationship. So, as your order quantity goes down, your ordering cost goes up. So, in other words, the higher the number of orders, so as you can see, the orders are going up, the smaller is the order quantity. So more orders means smaller order quantity, but more orders also mean more ordering cost. So in other words, if I have to draw a graph between order quantity and ordering cost, right? That graph is what we call an inversely proportional graph. When order quantity goes up, my ordering cost goes down. So as you can see over here, ordering quantity is going up from 0 to 1200, but cost is going down. Or vice versa, when ordering cost goes up, order quantity goes down. So the relationship between ordering cost and ordering quantity is what we call an inversely proportional relationship. And again, if you go back to your high school days, a directly proportional relationship is this, and an inversely proportional relationship is this. So this is an inversely proportional relationship. This relationship is something that I just showed you, which was for the holding cost. So I hope it clarifies the relationship between quantity and cost. So let's move on to our next slide. And again, the next slide basically describes the same thing, what I've just showed to you in this slide. So what does this mean for us? What this means for us is that now this is how our graph looks like for both holding and ordering cost. Ordering cost is inversely proportional. Holding cost is directly proportional. So the question that comes to mind is, why did we need to do this? So the reason we need to do this is because these two graphs help us track the graph for total cost. I'm just going to draw it in green. So if I add the two graphs up, which is if I sum the two graphs, so basically what I'm saying is my total cost is sum of holding cost plus ordering cost, right? Holding cost HC and ordering cost OC. So my total cost, total inventory cost is the sum of holding cost plus ordering cost, and that total cost curve is the green one, which I've shown here. Now, as you might see, that total cost curve has a minimum point. And that minimum point is called the EOQ point, or it's called the economic order quantity, because the quantity EOQ, the quantity that minimizes the total cost, I'll just write minimized total cost, is called EOQ. If you order higher than EOQ, if your Q is higher than EOQ, so you order something higher, your total cost curve, which is a green one, will have higher cost, right? Because after this point, the curve is going up. So if you order more than EOQ, your cost will go up. If you order less than EOQ, so if your quantity is less than EOQ, which is this side of the curve, your cost still goes up, right? Because this is the lowest one and the cost curve is going up. So that is why the concept of, oh, this is not EQQ, this is EOQ. Excuse me. So that is why the concept of EOQ is both interesting and important. Excuse me. If you order more than EOQ, your total cost goes up. If you order less than EOQ, your total cost still goes up. So the cost that minimizes total inventory cost, that quantity is called economic order quantity. So let's move on to the next slide. And the next slide will more or less show the same thing. Let me clear all drawings. So as I said in the previous slide, this curve is the sum of the two costs, which is sum of holding cost plus ordering cost. And that quantity that minimizes the total cost is called EOQ. Now, we have a formula for total cost, which is Q by 2H plus D by QS. Let's quickly see how did we get to this one. So, as I said earlier, the annual holding cost is the same as annual ordering cost when Q is equal to EOQ. If you order a quantity higher than EOQ, your cost is higher because the annual holding cost is more than the annual ordering cost. If you order less than EOQ, the holding cost is less than the annual ordering cost, but the total cost is still higher. So in other words, what this is saying is, if you are in this zone, so basically this is our cutoff, let's say this is our cutoff. If you order a quantity higher than this, then the holding cost is higher than ordering cost, right? And that makes the total cost go up. If you are in this zone, so if you order less than EOQ, then your ordering cost is higher than your holding cost. And then that is why the overall cost is up. Only if you're at this point or in this region, the two costs, the two components, these two and these two are closer to each other. And that is why this quantity is what we call the optimal order quantity. Okay, so now to the question of how did we get this formula? Let's move on to our next slide. So this slide helps explain how did we get this formula of total cost. So as I said, total cost is a function of holding cost plus ordering cost. Now, so I'm just going to write it here. My total cost TC is a function of holding cost HC plus ordering cost OC. Now, holding cost is over here, right? Holding cost is directly proportional to how much you hold. So the average amount of inventory in a cycle is Q by 2. And H is the cost of holding 1 unit of stock. So in other words, what I'm saying is, if my cost of holding 1 unit is H, my holding cost is how much is the cost of holding 1 unit times the average inventory I hold in a cycle. That is my holding cost. My holding cost is cost of holding 1 unit times the average inventory I hold in a cycle. So how much inventory I hold in a cycle? So let's say this is your cycle. It starts with 350. It ends at 0. Then the next cycle again starts with 350, goes to 0. So what's the average amount of inventory? The average amount of inventory is starting inventory 350, sorry. Ending inventory is 0. Average is 350 by 2, which is Q by 2. And that is what we have over here. So our holding cost is H times Q by 2. That's your holding cost. Now, ordering cost is, again, if the cost of placing one order is S, and refer back to the table that I created earlier, in which I was trying to show the relationship between order quantity and cost. So I said that if S is the cost of placing one order, so and we said in that example that S is 50, but that was just an example. So if the cost of placing one order is S, the total ordering cost is cost of placing one order times the number of orders you place in a cycle, right? The number of orders placed. Now, how do we find out the number of orders placed? So I'll quickly recreate the same table. So order quantity, number of orders, right? If the order quantity is 1200 and let's say the demand is 1200. If the order quantity is 1200, how many orders will you place? One. How do you find that out? D by Q. D by Q. 1200 by 1200, place one order. If you place an order of 600, how many orders do you place? The answer is 2. How do you find that out? 1200 divided by 600. If you place an order of 200, how many orders will you place? The answer is 6. 1200 divided by 200. So how do I find out number of orders? D divided by Q. So that's what I'll write here. So my annual ordering cost is cost of placing one order times the number of orders, which is D by Q. And that is exactly what we have here. D by Q times S. And then the total cost becomes holding cost, which we just found out is here. Q by 2H plus ordering cost, which is D by Q S, which is what we have over here. So that's the total cost. Now, how do you go from here to finding out the formula for EOQ? And that is on our next slide, but let me first clear all drawings. So now total cost is holding cost plus ordering cost, Q by 2H plus D by QS. Q is order quantity, H is holding cost of a single unit, S is ordering cost of a single order, and D is the demand. And usually the annual demand. But if the period is defined differently than a year, then obviously you'll have to use a different period length. So using calculus, we take the derivative of the total cost and set the derivative to 0 and solve for Q. And the formula for EOQ comes out to be this one, which is 2ds by h square root. Now, how do we get this? Most of you actually might not remember, but basically back in our high school days, there was a concept of maxima, minima. So the concept of maximum minimum was that if you take the first derivative of a function, the first and put that derivative equal to 0, that will give you the maximum or the minimum point of that curve. That is essentially what the concept of maximum minimum was. So basically, I'm just going to write the total cost equation. Total cost is sum of holding plus ordering. So holding cost is Q by 2H. Ordering cost was D by QS. So basically, I'm going to take the first order differential of Q because we want to find out the highest. We want to find out the quantity for which this function is the lowest, right? The highest or the lowest. So basically, we're going to take the first order differential of this and differential of this. So again, I don't want to belabor this point, but basically d by dq of q by 2h will come out to be h over 2, because dq by dq is 1, and d or dq of 1 over q, if you remember, is minus 1 over q square, and then this will remain ds. So basically this is dx by dx of 1 over x is 1 over minus 1 over x square. And again, you can consult your high school books for this, high school calculus. Okay, so basically then we set this equal to 0, because the maximum or minimum would be found at when we put this equal to 0. And then you solve for q. So basically this will be h over 2 is equal to d by s q square, which means if I solve for q, q square is 2ds by h, and then I just take the square root, and it will bring us to this equation. Now, this is the quantity that minimizes the sum of ordering and holding cost. Now, this formula will obviously be provided to you in the exam. This is something that you will never ever be tested. And again, this message is predominantly for my undergrad students. So this is beyond the scope of our course. But the reason I am giving you this explanation, because some students historically in the past have always asked me, how do you get the EOQ formula from this equation? So that is how we get the EOQ formula from this equation. So again, the formula will be provided to you. The formulas will be provided to you in the exam. When I say formulas, I refer to the EOQ formula, and I refer to the total cost formula. Now, with that said, let's move on. So basically, there are many assumptions that exist in the EOQ model. Those assumptions make this model very restrictive. Having said that, it has this formula is very robust, and it has wider implications for inventory management. We will relax some of these assumptions in our next discussion. But just to briefly go over the assumptions, we assumed that demand rate is fixed and constant in this. We will relax this in our next session. We assumed that lead time is constant. We will relax this as well. So no constraints are placed on the size of each lot. Again, this is something that can be relaxed as well. And basically, this assumes that the only two relevant costs are the inventory holding costs and the fixed cost per lot for ordering or setup. Again, once we relax these assumptions, this would be relaxed as well. So moving on, this actually brings us to an end of our discussion on, or theoretical discussion on EOQ model. Again, the entire model is built on this example. So yeah, I mean, if you have any questions, feel free to post those questions on the forum. Or when we meet next time, you can ask me questions regarding the EOQ model. I will go through one example of how to implement or how to use these formulas for our advantage. So this is this example talks about Museum of Natural History. So it has a gift shop that operates 52 weeks per year. So it operates around the year. Top selling SKU stands for stock keeping unit. SKU, stock keeping unit, is a bird feeder. So sales for the bird feeder are 18 units per week. The supplier charges $60 per unit. Ordering cost is $45. Our annual holding cost is 25% of the value of the feeder. And the management chose a 390 unit lot size. Now, the question that is being asked is, what is the annual cycle inventory cost of the current policy of using a 390 unit lot size? would a lot size of 468 be better? Now, that is essentially what the question is asking. Now, what I am going to do is I am going to create a blank slide, and hopefully that blank slide will help me create a no. Okay, so basically I've created a blank slide. So let's first write all the information that we have. So basically what this says is the sales for this unit, the bird feeder, is what we're looking at. The sales for the bird feeder are 18 units per week, right? So let me go here. So I'm writing a small d is 18 units per week, right? Now, we have been told that the museum or the shop operates 52 weeks per year. So my demand for the entire year is 18 times 52. So 18 units per week times 52 weeks. And let me see if I can run. So where did my mouse go? Okay, I'll have to actually let me put it 18 times 52 equals 936. And I guess it's better if I just use a calculator on my cell phone. So now we know our demand for the entire year, which is 18 times 52, which is 936 units. So 936 units. That is our yearly demand. Now we also know. Let me just write the formula there. We know that the formula for total cost is sum of holding cost plus ordering cost. Now holding cost is Q by 2H. Ordering cost is D by QS. We also know our EOQ. We also know our EOQ is 2DS by H. So first, let's just get all these variables. So we already have the value of D. Now, let's look at the holding cost for a single unit. So I'm going to go back for the slide. The slide says the holding cost is 25% of a feeder's value. So feeder value, what is the value of a feeder? So the supplier charges us $60 per unit. So basically the price that we are paying for a single unit of that feeder is $60. And our holding cost is 25% of this 60. So my holding cost is 25%, which is 0.25 times 60, which is 1/4 of 60. So that's $15. $15 per unit. And it says annual holding cost per year. Right? Okay. And then it says the ordering cost is 45. So we directly have the ordering cost. I'm just going to write here. And I know this is getting a little messy, but when I'll go to the next slide, it will be clear. And management chose a 360 unit lot size, a 390 unit, sorry. So right now, Q naught, I'm just going to write it Q naught, this is 390 units. And then it says, what is the cycle inventory cost of this current policy, right? Okay. And what a lot size of 468. So is Q1 is equal to 468 better. And I know you can't see this, but once I'll go to the next slide, you will be able to see it. Perfect. Okay. So basically, this is essentially what the entire question is, right? We have the annual demand, we have the holding cost per year, we have the ordering cost, which is $45. Right now, our ordering quantity is 390. And what they're saying is, for an ordering quantity of 390, what is the total cost? So I'm just going to call it the total cost 0, total cost not, because I wrote Q naught here, will be H holding cost plus ordering cost. Holding cost is Q by 2H. Our Q right now is 390. So 390 divided by 2 times H. H is 15, right? Plus D is 936. 936 divided by Q is 390 times S. So S is 45, right? And again, I am going to use my formula, sorry, my calculator. So 390 times 15 divided by 2 equals, divided by 2 or no? Okay, let me confirm it. 390 times 15 equals 5850 divided by 2 equals 2925. So this is 2925 plus, okay, 936 times 45 divided by 390 equals 108 plus 108. Okay. So my total cost is a function of holding cost plus ordering cost. Holding cost is 2925. Ordering cost is 108. Now, even before we move ahead, we know that this quantity is not EOQ. How do we know this? The reason we know this is because our holding costs and ordering costs are not the same. So remember, and let me draw it with a different color. So if you remember, this was Q here, this was dollars here, this was holding cost, right? And this was ordering cost. And the total cost was this. Now, and this is EOQ. This is EOQ, and this is the lowest cost. Lowest cost. Okay, so now if I, and I think the green one was good. Okay, so if I compare the two, basically what is being shown over here is that my holding cost is significantly higher than my ordering cost, which means we are somewhere in this zone where my holding cost is higher than my ordering cost. So in other words, the quantity that we are ordering right now, our Q naught of 390, is not EOQ. And what we can also see from here is that Q naught is for sure higher than EOQ, right? So then the question is, would a quantity of 468 be better? And the answer is no, it would not be better, because it would mean that we will, if this is 390, 468 is even more on this side. So how can an order quantity of 468 be better than 390? So you don't even need to calculate it. And the answer for this question is no, this would not be better. Let's just first calculate the total cost as well. So 2925 plus 108 is 3033. So this is our total cost. Now, the question is, if this is not the optimum order quantity and this is not the optimum cost, what is the optimum order quantity? And that optimum order quantity is EOQ. So let's try to find EOQ for this product, the bird feeder. So the EOQ is 2 times the annual demand times S divided by H. So 2 times demand is 936. 2 times 936 times S is 45 divided by H is 15. And this comes out to be, let me go back to my calculator. 2 times 936 times 45 divided by 15. So that is square root of 5616, which is 616 is 74.94. 74.94. Okay, so since you can't have 74.94 feeders, this will be 75 units. So the optimum order quantity that minimizes my total cost is 75 units. Now, if I change my ordering policy from 390 to 75 units, what will be my minimum cost? So I will call it total cost EOQ. So my total cost EOQ will be, again, using the same formula, Q by 2H, but now Q is total cost is holding cost plus ordering cost. Holding cost is Q by 2H. Ordering cost is D by QS. So I'm just going to enter the values. So Q is now 75. 75 times my holding cost is 15 divided by 2 plus D is 936 times S is 45 divided by Q is 75. So let's just write it here. Let's just calculate it. Okay, 75 times 15 divided by 2 is 562.5. 562.5 plus ordering cost is 936 times 45 divided by 75, and that is 561.6 plus 561.6. Now, as you can very clearly see, these two are very, very close to each other. The reason these two are not the same is because we rounded this from 74.94 to 75. If you use a much more accurate number, these will be exactly the same. So now these two are the same, which means we are somewhere in this zone. And if I add the two up, plus 562, this will comes out to be roughly 1124. So $1,124. So in other words, your total saving will be roughly close to I think $1,900. Yeah, 3,033 minus 1124 is roughly $1,900. That will be your saving. So with that said, this is how you apply the EOQ model. If you have any questions, feel free to ask me either by posting it on the forum or when we meet next time. Let me quickly go through the rest of the slides. Let me first clear all the drawings. Let me move here. Okay. So again, these are the same calculations. As you can see, we calculate that for order quantity of 390, the cost was 333. For 468, the cost was even higher. Again, in form of the graph, 75 is what we found out for the EOQ, and this is where they are currently right now. Currently right now, which is significantly higher than where they should be. EOQ is 25 units. If they go by EOQ, their cost will be roughly 1124 as against what they have right now. Now, this actually brings us to an end of our discussion on EOQ model. And for our next discussion, I would go to continuous review system. I've said this again as well. If you have any questions regarding the model, let me know, and we can discuss them either through the forum or when we meet next time. Thank you.